everyone. I warmly welcome you all to Phase 2 of Robotricks 2021, brought to you by the IEEE Robotics and Automation Society of University of Peradeniya, the student chapter of one of the most recognized and respected global organizations in the robotics and automation industry. In Phase 1 of the webinar series, Robotricks 2021, we had a great experience with robots, the robot simulation software, and also got a vast knowledge on robot control and path planning. On the first day, we promised you that you'll be able to create your own robot at the end of this webinar series. So here we have come to Phase 2, where you will be learning about sensor fusion, estimated design, and linear control techniques and implementation. Now we are already there in the beginning of Phase 2. I hope that you all will be joining us actively to delve deeper into the depths of sensor fusion. With that, let me introduce our guest speaker for today's session. He received his Bachelor of Science in Engineering degree with first-class honors from University of Peradeniya in 1994 with the award Professor E.O.E. Pereira Gold Medal for the Most Outstanding Graduate. Then he received his Ph.D. from the University of Northumbria at Newcastle Upon Tyne in the United Kingdom in the year 2000. Presently, he is the Director of the Information Technology Center at the University of Peradeniya and also a Senior Lecturer attached to the Department of Electrical and Electronic Engineering. His research was published in top journals in the world, including Automatica and PLOS. He has received the Presidential Award for Research Excellence several times and was a co-recipient of the NSF Award for the Best NSF Research in Engineering during the year 2019. He was a resource person for more than 50 CPD courses and workshops and also an invited speaker in many forums, including workshops for school teachers and students to inspire them with innovative thinking. So he's none other than Dr. Janaka Wijayakulasooriya. Dear sir, we are so honored to have you today with us. So I warmly welcome you to our today's session. Before handing over the session to our speaker, I have some announcements to be made for all the participants. We will be displaying a link in the chat box through which you can direct the questions to us so that we will make sure to answer them at the Q&A session in the end. Also, I request you all to remain with us until the end of this session as we are going to share an interesting news with you. So, without any further delay, I cordially invite Dr. Janaka Wijayakulasooriya to carry on the session. Over to you, sir.
Okay, thank you, Pala. Let me share the screen. Can you see the screen?
Yes, sir.
Okay. So when I, because to minimize the sound disturbance and everything, I have recorded the presentation. So, but feel free.
There is one unique property for everything in this universe. They change with time. For an example, consider your body. Over all these years, many parameters in your body, such as weight and height, has changed. Truly speaking, change is the only thing that does not change. The question is, how can we measure and represent these changing parameters? How frequently do we have to measure? How can we represent the measured parameters without losing essential information?
Good evening, everyone. It's always a pleasure to address a gathering of this nature. And also, I'm really happy to see that all over the Sri Lanka, students have got together and acting together to achieve further. I'm pretty much sure that this will further your knowledge and also further your experiences. Always when I see gatherings of this nature, it brings back some of the fond memories down in my memory lane, maybe perhaps 20 years ago. At that time, there were not many student societies in Sri Lanka. Even the IEEE was not started. And I was fortunate to be the senior treasurer of the Electrical and Electronic Engineering Society of University of Peradeniya. One day, a group of students came to me and requested me to propose a suitable motto for their t-shirt. And what you see in front of you is the motto that I have proposed. In fact, this is a historical t-shirt as well, because this is the first ever t-shirt uh, printed by the East, because they have given it to me. And when I see this nowadays also, it brings back me these nice memories. What I wanted to tell here is, when you act together, you can achieve further. This is not only valid for humans, this is also valid for sensors as well. So today, my topic is acting together to achieve further. Today, we are going to discuss how the sensors can be work in unison. Good evening, everyone. Today, I'm going to answer four main questions on sensor fusion. First, let us look at what is sensor fusion, or what do you actually mean by these two words. Then, where can we use sensor fusion? And also, when can we use fuse? So, when to combine sensors, at what level? And finally, but most importantly, how can we do sensor fusion? Because all the first three topics are not useful if we can't do it. So I would like to give you some brief about how can we start doing sensor fusion, or I would like to explain how to start it from the very basic fundamentals and then proceed upwards. Okay, so let us go on to what is sensor fusion. Now if I ask you a question, why do we have two eyes? Just think. Or why do we have two ears? There's a special purpose, because whoever designed us may not have put them arbitrarily. So why do we have eyes? Just to demonstrate this, I would like to show you a simple experiment that we used to do when we were in grade 3, 4 level, right? So just watch. Now what this guy is trying to do is, he is trying to put that pencil through that hole with one eye closed. Right? So he got successful only after few attempts. In fact, you also can try this and see if you haven't done this in your life. What have we done there? What is our eyes? Eyes are actually some kind of sensors, right? You all know in human body we have few sensors. Eye is one of the most important sensors that we have. Ears, right? Then our taste buds, nostrils, or the sensors that you get from nose, smell, So as human beings, we also have sensors. And by fusing them, we can get more information. For example, now what was missing when when this kid was trying to put that pencil? He has lost one sensor, and because of that, for some time, he has lost some information. That is the depth information. If you consider our ears, it's the same story, because if you lose one ear, you may have felt that you don't feel this depth of sounds, right? You only hear sound, but you don't feel the depth. So why these kind of things are happening? Because the depth information are cleverly transmitted to our brain like this. So this example itself shows some basic idea about fusion, right? So you are getting the readings through two sensors. They are fused in your brain and create totally new information called as depth. Now, nowadays you may have seen these kind of pictures. Well, this is not actually sensor fusion, but fusion of sensor information with time lapses. Those who know how to take a photograph of this may have experienced how to take something like this. So what you get is uh, information coming from the sensor of your mobile phone, that is the camera sensor, with some time lapses, right? Then they will be combined together to generate the picture of this nature. Maybe they are using the other sensors in the phone as well for this particular thing. For example, in your phone you have gyroscopes, accelerometers, right, which will detect the movement, and all these will be fused together when you create a picture of that nature. Another example.
Cars
These
are
are
on the road.
the future
They use a
transportation
range
of
of
the world,
technology
unmanned
we've built from the
vehicles.
ground up to understand the world around
Now,
them
if you
and
take a
get you where
modern
you need to
car,
go.
Sensor
not
beams
even something
radiate from the
like this,
car.
You're about to
even
see how it
just a
all
normal car,
works and what it feels
how
like
many
to ride in our
sensors
car.
do
Waymo
they have,
drives through an
right?
intersection.
The vehicles are
As it
full of
drives,
sensors.
Waymo uses LiDAR,
They are
which sends
detecting
out millions of laser
various
beams
things.
per
They are
second
sensing the
to build
driving
up a
environment.
detailed picture of the world
Some of
all
them are directly
360 degrees around
controlling
it.
the vehicle.
It
Some of
also
them
uses
are
radar
assisting
to
the
detect how
drivers
far
in
away objects
maneuvering.
are and their
For
speed.
example,
And
sometimes if the
high-resolution
vision is not
cameras
clear,
detect
right?
visual
Those who
information,
may have
like whether a traffic signal is red
driving
or
in the
green.
night time
Traffic signals light
may
up.
have felt
It then
that
combines
they
all
don't
that
get
data
some
to
information.
understand the world
They
around
don't
it.
see some
For
pictures.
example,
So
in this fraction of a second, it knows
kind of
exactly where it
fusion that
is
you
on
are
the road.
using in these places
It
will
can
help you.
also identify
Also,
everything around it
sensors which
in
will
full
extract
360
all
degrees,
the moving
Labels appear on
objects,
objects.
right? Different
and
road
then
signs,
predict what those
and
things
also
might do
detecting
next.
road signs and
Projected paths appear.
converting those
And
information
it
not
doesn't
to
just do
eyes,
that for
because
the
your eyes
objects
are
you
too
and I can
busy
see.
when you are traveling,
It can do that for
and maybe
things up to 3
converting
football
them so
fields
that
away.
you
From a
can
bird's
grasp
eye
it
view,
through
graphics
your
highlight
ears.
objects.
What makes everything you can
All
see right
this
now possible
comes
is
under the
experience.
purview of
Waymo
fusion.
has already
So
self-driven
fusion
millions
is
of miles on
basically
complicated city
mixing
streets,
information
and it's constantly
or
learning from every single
making
mile
them
it
work
drives.
in
Back on
unison.
street level,
Actually,
Waymo
both of
maneuvers.
them, while watching that video, right, you may have felt you are getting information from two sources, right? Me also speaking, and then the video also has its audio file. But amazingly, some of the words we can understand, right? That shows the best fusion algorithm in the world is in our brain, right? It can mix information, and also it has the power to unmix information, which no machine has achieved it, right? So although it has happened due to a mistake, right? I couldn't switch off the audio of that video, but I think that from that also we can learn what kind of machine is our brain. So for most of the sensor fusion algorithms that we use in our world, we take ideas from this amazing device called as the human brain. And also not only that, we get the ideas from various other animals, right? Especially bats, right? How they are combining their auditory information to navigate. I think many of you may have learned how bats are navigating during night, right? So like that, there are a lot of ideas that we can get from nature. Collaboratively to get more information. So I don't have to explain it to you, right? In a modern car, you have all these kind of sensors. There can be in-car sensors, acceleration sensor, ambient sensor, side sensor, pressure sensors, speed sensor, vision sensor, and also uh, rear distance sensor, right? And also there are sensors which will detect the condition of the driver, whether the driver is sleepy or whether he or she is healthy, right? So all these information is combined together to get a better understanding of the driving environment. And even us, right? When the information comes to our brain, we also do sort of fusion. Now forget about all these modern cars. Even if you are driving a very old car, right? The way we drive, just try to think of how do you drive a car when you are driving in a hilly or misty area. If you have gone to Haputal area and if you happen to drive in early morning, you know the whole place is covered with mist, right? Then unknowingly you put some weight onto your ear also. Usually we drive mainly based on the information that we are getting from our eyes. But when we are approaching a bend or when we are driving near uh, some place which is unclear, maybe mist due to mist, right? We are combining our senses. So sensor fusion is something which is not distant from us. It is very close to all of us. And it's very interesting to see how our natural sensor fusion takes place, right? When we fail in one sensor, another sensor develops. Okay, so now let us try to get some more sort of theoretical idea about what is sensor fusion. Usually, using sensors, what we try to do is we try to get some information about some unknown parameter x, right? There are a lot of unknown things in this world. For example, let's say this is the temperature inside the room, or it can be the, the, the condition of a patient. For example, whether you have COVID virus inside your body or not. That is X. Then we can't directly see those things, right? Even we don't know whether there is something called as temperature, although we talk about temperature, but we believe that there is something called as temperature and we want to measure it. So how do we measure? We take some observations, right? So to get observation, we use sensors. Even your thermometer is a sensor, right? With mercury column, it is converting that what is called as temperature into something which is observable. Let us call it as Z, right? So now X is converted to Z using sensors. Even if you take a modern sensor like thermometer or optical sensors, right, which will show you the temperature using color information, the same thing happens. The temperature value will be represented by some external parameter which can be observed, right? Then what are we going to do? What's the next step? Sometimes instead of taking one measurement, to get a better idea of the environment, we can get many measurements. For example, if you want to measure the temperature inside a room, if you have one temperature sensor, you will get the temperature reading of maybe a particular place. It may be not accurate to the other corner of the room. So in bigger areas, you are using several sensors, right? So usually this measurement domain, let us assume it is an n-dimensional one. So you get from 0 to n minus 1, that is n number of measurements from this unknown entity. So if I go back to the question, we have something called as x, let's say the temperature in the room. And to estimate the temperature in the room, we are getting n number of measurements. Let's say you have 2 temperature sensors. So n will be equal to 2. So you will have 2 measurements, Z0 and Z1. Now what we are trying to do is use these measurements and combine them somehow and try to get an estimate of this unknown quantity, right? Always when you take a measurement, this is what we are doing. If you carefully look at this also sensor fusion, because we have combined that information together to get a better estimate of the room temperature, right? So one of the simplest algorithms that you use for sensor fusion is, I think everyone knows, averaging. But have you ever thought, why are we doing average? Or what is the explanation behind averaging? We all do averaging, right? Why we do average? What is the mathematical explanation behind averaging? Well, in all these algorithms or methods that we are using, what we are trying to do is, this is the real ground truth. Ground truth means the real value which may be there. And then using the sensor measurements, we are estimating some value. Of course, in the real world, always there will be an error, right? We can't estimate anything with 100% accuracy. If you are really lucky, it will happen, but always there will be a difference between the reality and what you measure. So as a result, there will be an estimation error. Let's call it as E. So our prime target is, in all these algorithms or methods that we use, is to minimize this estimation error, right? If there are many parameters that you are measuring, then you can't just minimize one error. You have to estimate all the errors. So we define a term called as estimation error covariance. These are just technological terms. So basically, in all these sensor fusion algorithms also, what we are trying to do is to reduce this estimation error covariance, right? So this is applicable for many of the practical examples that we are going to see today. But in addition to that, there are other type of applications where it is not always trying to minimize this error, right? So let us try to have some idea about different types of sensor fusions available. Usually we classify them into 3 main categories, but of course there can be other categories, right? And also there can be overlaps between various things, but for the easiness of understanding the subject, it's always useful we divide. The first thing is competitive fusion. Let's say you have an object or a particular environment to be monitored, right? Again, think about that 2 temperature sensors. So you have 2 sensors, S1 and S2, which is measuring the same thing, right? And then you have a fusion method called as competitive fusion. You know what is competitive? In the competitive one, one approach is you take the best one, right? For example, if I rely one sensor than the other sensor, then I will take it. Or forget about that, right? Suppose you want to measure time. What do you normally do? You ask from few people. Why are you asking from few people? Because you want to get this fusion. The person whom you trust most, you believe, right? That is voting. And then you get the idea about this environment that you want to measure, right? So here, what we mainly look at is the reliability and accuracy. So this is what I was talking before. We are mainly concerned about estimation error covariance. In the next one, uh, we will go for complementary fusion. What do you understand by complement? Right? And also there is another fusion called as cooperative fusion. Let us try to see some examples of these. Right? First, we will take the competitive fusion. In competitive fusion, as I mentioned before, you are trying to combine information, right? Let's assume that one person tells you one time. And when you ask the time from another person, he or she will tell you a different time. Now, based on how much you believe on their times, right? Let's say T1 and T2, based on how much they are accurate, you may take one of their time, or you may take the average of their time, right? So that also a possibility, right? For example, if someone is using a very accurate digital watch, you may tend to select that. But if it is two different people having two different times, perhaps uh, rather than selecting T1 or T2, you can get some rough idea about the time by combining the two information, right? So that also competing, this combining, because they are also each of the sensors. Now here, although I call it as competitive, you are giving equal weight to them, right? So each of them are equally competitive. But also you can do sort of weighted average also, right? In that way, the sensors are made competitive, but you weight them based on how much you believe in each of the sensor, right? When I say how much you believe, it may depend on their fast performance, right? So you can see a very simple sensor fusion approach. Now, next we will take the complementary fusion, right? In complementary fusion, what we do is we try to monitor some environment with some overlapping, right? For example, just try to think of some application, right, where you want to get the complete information, because only when you have the both sensors, you have the complete. One example I have taken here is the CCTV, right? So suppose one CCTV is covering one area, another CCTV is covering another area with some overlapping, right? So only when you combine both, you get the complete picture, right? So we go for complementary fusion when we want this completeness, right? So now we have done two of them, competitive and complementary. So let me erase this part. And the next one is cooperative, right? Cooperative is the one most interesting one, because in cooperative fusion, you will be able to get information which cannot be, uh, measured by individual sensors, Now, for example, if you take the complementary type, right? If once, let's say one CCTV goes off, at least you have this information. But in cooperative, we need all these sensors to get the final figure that you want to get. One of the best example is triangulation, right? Triangulation means you have various sensors and using them you want to estimate the location of something, right? So always cooperative sensors will provide you something new information, right? For example, take a mobile robot, right? How do you usually estimate the position of the robot? Well, there are many methods. Most popular method these days is using accelerometers and gyroscopes. But in addition to that, one method that we have been using for a long time, especially inside building, is you send some signal by a sensor, wait for the reflection, and then you measure the distance to uh, the surface it reflects, right? And using that, we try to estimate our position. So this is one example of triangulation where you need few sensors, right? I mean, at least 3 sensors to do triangulation. There, what we do is based on the information that you are getting, you are trying to create new information. But that new information cannot be created with individual sensors, right? All the 3 sensors should be there to estimate the position, right? So these are the basic types of sensor fusion that we have. Okay, so I think now you may have got some idea about what is sensor fusion. Next, let us try to see where can we use sensor fusion. So yeah, where can we use sensor fusion? Of course, if you go to the internet and search for applications of sensor fusion, I'm pretty sure you will find loads of sensor fusion applications, right? It can be sensor fusion in vehicles, many modern things, right? So I don't have to teach you how to go and search internet because you may be experts than me. So please go and see what are the new types of sensor fusion applications which are coming out, right? But I don't think my duty here is to take you through all this web material because that will not serve the purpose if I use some other's result and try to give you an idea. The main idea of a keynote speech is to share my experiences, right? So while leaving you to follow all these things, at least at a glance, right? Because there are very interesting things out there. What I would like to do today is take you through some of selected projects that I was involved in during the past and tell you how we were using sensor fusion in different ways to achieve our goals, right? I think with that, I can give more information to you than going through downloaded material. Okay, first I would like to select this project. This was the project which won the first place in IESL Raspberry Pi Challenge in 2017 in the Techno Sri Lanka Award. And now I am happy to say all of them are doing their PhDs. And this is what they have been doing, right? Now suppose you have a mobile robot like this, right? This is an omnidirectional mobile robot which can move in any direction. So they have developed it. But then they wanted to generate a map of this room, right? So the main idea of this one is you have to generate the map of this room while traveling through this building, right? And also, we have given another challenge. You have to do that scanning or traveling through this with the minimum time. So you have two challenges. You have to generate an accurate map, and also you have to do that within the shortest possible time. And they came up with very nice sensor fusion here. The Sachini was working on stereo camera based sensor fusion, and Samira was working on this mapping part, right? So he combined two different sensors, right, to get this map. First, to get a rough map, you are using one sensor. I will play the video later, then you will understand. So then the other one, Bhavant, right, he was using another sensor algorithm to estimate the location of the robot, right? So this is how it was done. So think you are getting different information from these sensors, ultrasound maybe, right? Or they had a LiDAR sensor also on top of the, here you can see it is on the top of the vehicle, right, where you are using laser beams. By combining all this information, they are generating this map, right? And also, they have to make decisions at certain places. For example, when you come to a junction like this, where you have two parts, where to move first, right? So there were a lot of fusion happening here, right? And also don't forget about our challenge, do it in the minimum time. So they have a rough scan first, and then they have a more detailed scan. So I think you will be able to see their approach if you watch this short video.
Autonomous navigation, search and rescue, planet exploration, underground mining, disaster relief. Simply places where human access is restricted. Solution: vision-based mobile robot for reconnaissance. Powered by Department of Electrical and Electronic Engineering. The task of mapping an unknown environment in 3D has been addressed through three main sections as replicating human vision, decision-making and mobility through an enhanced holonomic mobile platform.
First, with stereo camera, we tested display map generation and then depth extraction, but they consist with noise. So we moved to RGBD sensor, where 3D map of the environment was generated by point cloud stitching.
Replicating human decision-making ability was achieved by classifying sensor data to identify gaps, closest region first, smallest gap first, adaptive stepping, and intelligent neighborhood identification are the key features we introduced in and implemented.
To correct the erroneous localization, first simulate transform method was tested, but it wasn't efficient, so errors were successfully corrected through the particle filter-based approach. To fix the incapability of mobile agent to track the reference, a separate control strategy was developed.
Scanning the area. Mapping initiated. Looking for dead ends. Selecting the unexplored gap. Finding the minimum width gap. Checking for probable collisions. Mapping completed. Returning home. Analyzing neighbors. Calculating the minimum cost node map. I'm at home. Deploying 3D mapper.
Intelligent exploration uses an adaptive and intelligent method of exploration and understanding of the environment. Laser ranging based localization, no GPS or magnetometers used. This can be used in deep caves, underground mines, other planets, etc.
Sorry. I think in that project you may have got an idea how different kinds of sensors are used in unison for generating more information. As the next project also, I would like to select another very interesting one, because it's also a robot, because I was trying to select some examples related to robotics, because this session is organized by as a part of an activity of IEEE Automation and Robotics and Automation Society. So the next one also interesting, and also it made a very good achievement also. So that is why I'm selecting that. Sorry. Yeah. I don't know whether you know about this journal, Automatica, one of the most prestigious journals in the world, especially confined to the robotics. So if you are a person working in robotics field, this is where you should target, because this is a meeting place for the leading people in the world in the subject area of Automatica. Now, few years back, we were able to publish one of our undergraduate project, which was again continued as a postgraduate project in this journal, right? And now this lady who has done that project, Udari Madhushani, now she is doing her Ph.D. in the Princeton University. Now, and also she has won the Presidential Award for this research in that year, together with us, me and Dr. Maitripala, one of the leading person in Sri Lanka at the moment in robotics area. So I would like to talk next about how sensor fusion was used in this project, right? In fact, what we have given her is a very challenging task. We have asked them to develop this spherical robot. So in undergraduate project, she has worked with another guy, Ranavira, and both of them have done a very nice prototype model. And then she further developed it during her postgraduate before leaving for the PhD. And basically, this is about the spherical robot.
Method,
usually you may have seen robots
which can provide
which have
only the
wheels,
directional nature to the robot.
but just
For the
have a look at
two-dimensional
this.
model also, initially a mathematical model was created based on Lagrangian equations. It involved solving a set of really complicated nonlinear equations. The plant simulations were done using MATLAB Simulink to check the behavior of sphere for a given input torque. Since the system is highly nonlinear, a nonlinear PD controller was proposed to use. The simulation results of the controller verifies that sphere can move in approximately constant velocity with minor fluctuations. When making hardware for the two-dimensional case, initially the design was done using SolidWorks. It mainly includes 4 pendulums attached to geared motors and 2 batteries at the center. In the prototype, STM32F4 was used as the main controller board, and Arduino used for communication and feedback calculations. A Bluetooth module was used to create a wireless communication link. Accelerometer and gyro module placed at middle to obtain angle measurements, encoders and optocouplers used to get motor speeds and positions, and motor driver ICs and batteries. A special cage was made to hold the batteries and gyro and accelerometer module at the center. All the electronics were finally compacted inside a fiber hemisphere in a way that they don't collide with pendulums. Thereafter another hemisphere fixed to complete the sphere. After the controller is finalized, it will work inside a discovery board and control signals will be provided wirelessly, via a Bluetooth link. Currently an Android application is used to control the motors, in an open loop, via Bluetooth. Even there were slight variations, the robot was moved as expected. Now we are working on designing a controller to drive this robot in a given path with a given velocity.
Okay, you may think, what is this, right? It's traveling like a dunkard, right? But believe me, this is one of the most challenging robot controller. The reason is, compared to the other robots, this is not moving in a plane, right? This is always rotating. So when you rotate, all your gyroscope data and accelerometer data, they becomes really complex, right? So even we are happy that we were able to take it even like a drunkard, but we have done this because of these challenges, right? Because we really like to face those challenges, and then we wanted to prove that some of those challenges can be overcome, right? That's why even that was selected to be published in the Automatica journal, and this is one of the most cited papers from us, because this is totally different experience, right? So here you may have seen the sensors. What were the sensors inside this? We had accelerometers, we had gyroscopes. In addition to that, we had other sensors, right? Encoders and so on. So in order to get our position correctly, because if you want to navigate a robot, you need to identify its position correctly. Then also you need to identify its acceleration, right? And also in this particular one, there were more challenges because this is rolling, not moving in a plane like other robots that you have seen before. That robot is moving on a plane, right? Maybe there will be some climbing and so on, but basically it is going in a constant plane. But this robot is always rotating, right? So the sensor fusion algorithm also was very challenging and difficult. And as the next one, I would like to select a totally different one. Sometimes you may have seen this in movies, right? And get this wow effect, right? Uh, okay, this kind of advanced technologies are in the world. But why I have selected this one is, I wanted to give you the confidence. If you cleverly think, we also can do these things, right? I'm not promoting the warfare or any other thing, but the bitter truth is, it is due to the military some of the technology has developed, right? Now if you take a modern day soldier, he will be wearing lot of uh, sensors around him, right? There are some sensors too, like which have been shown in this slide, which I have downloaded. This is not my work. So they are monitoring his health condition, right? His biomedical signals. For example, headband EEG and oximetry. Acoustic. For example, using acoustic, you can identify voice stress, right? And also what they are speaking. What are the words that they are speaking, right? Uh, then there were dead reckoning modules. You want to identify whether what is the condition of this person, right? And also EKG, EMG based sensors. Body core and skin temperature, because in warfare, that is one of the main challenge that they face is their body temperatures increase significantly, In fact, in Sri Lanka during the Northeast War, at one time I remember in Alimankada, many soldiers died because of dehydration, right, when they were returning. So these were monitored, right? So like that, there are a lot of sensors on their body. In addition to this one, it will be really useful if you have some sensors to locate them. Now, one of you may ask, why don't we use GPS? Yes, GPS is a good technique, right, which is commonly available nowadays. But one of the main challenges in GPS is, in some places, GPS not working. In some places, the accuracy of GPS goes down, right? For example, if you go to a place like the Navy harbor in Trinco, for some reason inside that harbor, the GPS not working. So we want to develop a sensor for tracking these people. So actually, GPS also can be used. What one can do is you can fuse GPS with the sensor that we are developing, right? So this research I'm doing as a postgraduate project with a student from the Defense Research Unit. So what she want to develop is a device to be wear around their belt, and this has to estimate the position of the soldier, right? Now, basically, for the moment, we are only confining to accelerometer data and gyroscope data. So we have this sensor, and then we are recording the values, right? Of course, when things are very smooth, you will be get something like that, right? When they are working. Another important thing, right? You can even detect what they are doing also, right? The signals that you are getting when you are walking may be different from signals that you are getting when you are running or when you are staying. So not only their position, their activity also can be detected using these sensors, right? So these are the accelerometer data, and also we are getting the gyroscope data, and also there is some offset because when you are working with sensors, this hardware stuff. So we want to remove that, and finally this is the gyroscope data. Now what we want to do is we want to combine them together, accelerometer data and gyroscope data, and the path of this person traveling has to be estimated up to some accuracy, right? So this is sensor fusion for localization, which is very important in mobile robots. And also we can do event estimation. Event estimation means whether this person is jumping or whether this person is running or walking, things like that. And very importantly, abnormal event detection. Abnormal event means the normal event maybe they are walking, jumping and so on, right? But suddenly this person start running in a different direction. So you know there is an attack, right? So that kind of information also we can extract from this, right? In fact, we are not going to go up to that level in this particular research, but in a different research that I'm going to talk now, we have been focusing on this abnormal event detection, right? So by even not combining sensors or sensor fusion, by fusion of different research also we can get better result. So my next selection is again from the uh, undergraduate project. This was done in 2014, and it had a great achievement that also I should mention in IEEE in International Conference on Industrial and Information System, which was held in India in IITs, right? Where there were many postgraduate projects were presented. These three were capable of winning the best paper award there. It was a huge achievement, and also that year they won the IESL Best Undergraduate Project in Sri Lanka as well. Here what they are trying to do is they are trying to use vision sensors to estimate the location and track a person. The same thing that we were doing, they are using gyroscope, but by combining these two, I think we can get a better idea about the environment, right? So don't forget what I told at the beginning, acting together to achieve further, right? Now I am happy to say all these three guys, they have done their PhDs. Two actually have completed and got their PhDs. One is doing the writing up, right? So while talking about these things, one main message I want to give is what you can achieve as undergraduates, right? Because when you see some technology, maybe sensor fusion, deep learning, or whatever, what we are used to do these days is just get this wow factor, right? There is a technology Marai Machan type idea, and then finally get amazed, and that's it. But I want to give you the confidence, if you really take it into your hand, you can do things, right? Because it is human like you who are the creators of all these wonders. The next project I am talking about also will be taken from another project that I'm doing it. Again, this is a postgraduate project with the military research unit in Sri Lanka. There, that also a girl. What she want to do is they want to develop this tripod-based sniper. This is the sniper gun. They want to develop a simulator for this because in training, when training this thing, they can't always waste bullets, right? So what they want is they want to develop a gun. So you just aim it at the target and trigger it. No bullets will be used, but it will display on the computer screen whether you hit the target or not, right? To do that, they want to correctly estimate, very accurately estimate the yaw and pitch of this gun, right? So that is what we are doing. And here the fusion comes because this is the basic prototype that they have developed. Uh, First, you are directly measuring it, right? The two angles that you want to measure, you can see using, let me show you here. Yeah, using these two encoders, you are directly measuring. Then you may wonder, what is sensor fusion here? You are directly measuring something, right? But please keep in mind two things. One thing is, all these are noisy measurements, right? In some applications, this may be okay. But when it comes to some application where we need to be very precise, the noise will have a significant effect on these encoder measurements. So in addition to these encoder measurements, they are using IMU sensors, right? Basically, you have gyroscopes and accelerometers, magnetometers, right? We keep on testing those things. So various sensors are there. And then by combining all these things, we want to because this is what we have to estimate, right? When you put this gun like this, where it goes and hit in the target, right? So that has to be shown on the computer screen so that this can be used by the people to take their aim, right? So this is about, unfortunately, killing people, right? But then uh, I want to talk about giving life to people, right? Now I think this is one of the happiest moment in one's life, right? This is the point where a mother receives her child. But believe me, this is a very complex process, right? Although you will feel happy after everything, the pain that you have to go through, and most importantly, the risk that you have to go through is enormous, because it's a very complex process, right? If anybody is interested, you can read what are the chemical reactions going through your body and how they are affecting the mother, how they are affecting the baby, right? So you have various things like fetal stress, maternal stress, right? I mean, this is one of the most complicated process in this world, I should say, right? So one of the things that the doctors advise the mother is to check whether the baby is okay. They always ask to, maybe after few months, they will be asked to count the number of kicks, right? So the baby will always doing some kicks during when you are in womb, and the mothers will be asked to count them, right? And then they will be asked to detect whether there are any abnormal patterns. For example, if a baby is not kicking for some time, they are asked to consult the doctor or admit to the hospital, because sometimes it can be due to a very serious case, right? Most common case is the cord, right, which is connecting the baby to the mother, get wrapped around the neck of the baby, right, when they are moving in the womb, right? So you are going to suicide while you are in womb. So in order to prevent that, the mothers will be asked to count. But unfortunately, when most of them are working mothers, so sometimes they will be in different situations, right? So they uh, fail to count this, right? Although the doctors advise, the mothers are not doing it according to the doctors. So uh, one of the doctor in VOG in Peradeniya Hospital, Dr. Chatura Ratnayaka, he wanted us to come up with a solution for that, to identify the mother's kicking, right? And one reason for selecting this project to demonstrate it to you is, again, this journal. Right? This journal is one of the top ranked journals in the world, plus one, uh, which publish some multidisciplinary projects, right? So this is a huge achievement for us also, because this is a project between engineering and medical. And then I think 1 month ago, we were able to get this publication, right, in July 13th. So that is why I have selected it here. And also this shows the application of sensor fusion, right? Now this is what they have done. Initially, during their undergraduate time, they have developed this device to monitor the baby. And then it also contains accelerometers and other sensors, like we were using gyroscopes even. So all these sensors are coming to a device, and there you have to analyze them and tell whether the baby has kicked, right? Right. So these are some of the very basic accelerometer data you get, but they contain a lot of noise, and also you get all these fluctuations due to various other activities, especially when the mothers are laughing or when the mothers are doing other activities, you get some fluctuations here, right? So this, I think they have tried to visualize it in different form, putting them onto. Now you can see with different activities, you go into different areas of this 3D map, right? So basically, this is not a difficult graph. This is basically the x-axis, y-axis, and z-axis data that you are getting. Then by fusing this data, fusing means combining these three accelerometer data, they were getting signals during various events. So this is what we actually want to detect, fetal movement, right? So whether the fetus is doing well there, right? But then when the mother is laughing or some other emotions, you will get things like this on the accelerometer, right? And also when the mothers are breathing, you are getting this kind of signals, right? So we got them by fusion of those signals and then those sensors, and then based on this, now we have to do another kind of thing, that is identify whether the mothers are doing, right? So later I will be using this. Now, since we can't directly see anything in this one, we have to always go to other domains like uh, spectral domain or frequency domain, right? So this is the short time Fourier transform of the same signal, and in that mode we were capable of identifying certain differences, and then we capitalized on that and uh, written algorithms to detect, right, whether it is a fetal movement or maternal laugh or maternal respiratory movements. And although it is not that successful, you can see the percentages are somewhat low, but this was accepted because of the importance of this work, right? And this is the summarized result. For example, they have tested for 6 mothers and they have compared 3 algorithms, because algorithm 1 is not included here. In algorithm 2, you get 93.55% accuracy. So like that, but you can see algorithm 3 is performing bad for mother 1. But the same algorithm may perform well for another mother, right? So please keep this in mind, because I'm going to use this to explain another thing at a later stage. The thing is, these 3 sensors, right? I mean, these algorithms also we can take as 3 different decisions or 3 different sensors. So these 3 different decisions perform differently for different mothers, right? So please keep that in mind. Okay, so I think I have given more than enough examples about where we were using sensor fusion, right? There are a lot of other examples as well, but due to time limitation, I have restricted to some published and award-winning projects only, right? There were too few award-winning, but I couldn't include them here. But I think you can get an overall idea where you can use. But more importantly, if you have got the idea, that you also can do them, because it was some students like this, few years seniors to you, have done this. So if you also can do this, right, I think I will achieve the objective of my presentation today. So I wanted to give that confidence to you. Okay, third thing, when or at what level. So I'm not going to spend a lot of time on that topic, because I want to spend a little bit more time on how, right? So let us see basically at what level are you applying this fusion. Basically, we apply fusion in 3 different levels. First, raw data level, right? Then feature level, and finally decision level, right? So in raw data level, you can see from, if you remember that fetal project, we are getting different sensor readings, right? Then we apply fusion and we get these 3 waveforms. And that is an example of raw data fusion. You are getting raw data and you are combining the raw data to get some new type of information, right? So that is what you mean by raw data level fusion. Then we come to feature level fusion. In feature level fusion, rather than applying the fusion algorithm on data, raw data, first you extract some features from the data, right? For example, I can find out what is the spectral energy in a certain band of this signal. Then you combine that data, that is the extracted features will be fused together to get more information. Then finally comes the more important thing, decision level, right? In decision level fusion, I ask you to remember these things. different sensors or different algorithms perform differently and they give different decisions. How can you combine these decisions? So you are not combining this at raw data level or feature level. You finally make the decision using each individual sensors, and then only you will make a decision, right? Now, if you take the algorithm 2, 4, and 3, these three, right? Uh, let's say algorithm 2 has decided the mother has laughed, but algorithm 4 says no, she has kicked. Algorithm 3 also says she has kicked, right? How many times do we experience this in our normal life? If you go for 3 different doctors when you have a disease, they will tell 3 different things. Then how can we come to one final conclusion? We have to do fusion. So the decision has to be fused together, right? So what we do in decision level fusion is we combine decisions together, right? The most commonly used theorem is the probability theories. You based on probabilities, you will try to estimate what is the most possible decision, and also you can add some error, the confidence level for your decision, and tell, okay, I'm 100% confident about my decision, or I'm 90% confident, something like that, right? So decision level fusion also one way that we are doing fusion. And you may wonder, why do we need decision level fusion? Because uh, isn't one decision enough, right? For example, if you look at that table, I don't know whether you can see it. Algorithm 2 proves to be better than the other two algorithms. For the 6 mother, we can't conclude with 6 mothers, but it seems to be good. So you may ask, why don't we just go with algorithm 2 only? No, because we can always prove using statistics, when you combine more information, only thing is you have to decide how much weight you give to each decision, right? For example, let's say you go to 3 doctors to get the solution to a problem. One doctor say, okay, don't do this operation. Other two says, do this operation. Then how do you come to a decision? You consider all of them, and also you consider their reputation, and then use them to combine the information and come to a final decision, right? The same thing. Okay, I think that is enough about when. So I would like to talk. Next, let us see the most important thing, that is, how can we do sensor fusion, or how can we at least start doing sensor fusion, right? So most of us nowadays used to use available libraries or whatever the algorithms and do fusion. That's fine if you want to just achieve your final goal. But I really recommend at this level, right, try to understand the very basic fundamentals and build up from that level. That is important because then only you can propose your own algorithms. Otherwise, you always have to be limited by the libraries which are available, right? So if you want to do some breakthrough innovations, start from very basics and get very basic idea. So that is what I am going to do in the next section. How can we do, or how can we start at least, right? Let us start with a very simple example, right? So I had made it as much as possible simple because then you can get the basic idea, right? So let us consider some sensors which are used to measure, let's say, temperature, right? Now, let's say if you take a room, right, there are two different temperatures at two different places. right? And you connect two temperature sensors at those two places, right? Now suppose your sensor is converting them to something which can be, let's say, recorded in a computer or microprocessor or something, right? Let's say, so for that you have to convert this temperature into a voltage or a current, right? Usually you have various types of sensors which will do that for you. So at the end of the day, you will get two voltages representing those two temperatures, right? But then in this room, there is something called as temperature which we want to estimate, right? So, but at the end of the day, we are getting just voltages. So how to use these voltages and try to estimate what is actually there? So we call the actual temperature is, let's say you want to operate the air conditioner. So what is the temperature inside the room which will be used for that decision making, right? So this is usually we call as the ground truth, right? It may be the average temperature inside the room, right? If there is a spatial distribution. So anyway, by using these two voltages you are getting, I want to estimate what is capital T. I want to finally give a value of this temperature, right? And during this process, we call this as forward conversion. The temperature will be converted to voltage value through some circuit, right? It is by going through F1 and F2. If you are using the same type of sensor, F1 and F2 are same. And also we can do things like that. I told you not only spatial distributions like this, even these two can be time distribution or temporal distribution. Temporal distribution means you take a temperature value, then after, let's say 1 second, you are taking another temperature value. That also called as fusion, right? There we are doing temporal fusion. Here we are doing spatial fusion, but the basic theory is there. So if it is a temporal fusion, we will have same function here because it's the same sensor, right? If it is spatial fusion where you are using two different types of sensors or two sensors with different properties, then there will be two mapping functions like this. Because you have to convert temperature to resistor and then convert resistor to a voltage. Now, using an inverse function or reverse function, we have to convert this back to an estimation of T1, right? So if T1 is the temperature of a particular time or particular spatial point in the room, I have to now develop a inverse function for doing that, right? So let's call it as G1. Similarly, I have to do that for uh, V2 also, right? Now, for example, why we call this as T1 estimate? Because what I estimate here is not exactly same. So, for example, if you take a RTD sensor, right, which is a resistive-based temperature sensor, you know this famous equation that you have learned in A level, which represent the resistance is equal to R naught. R naught is the resistance at 0 into 1 plus alpha T, where T is the temperature. But then you may have seen there are more accurate equations of this nature, right? 1 plus alpha T plus beta T squared, and there are more terms. So this equation is just an approximation, which means this conversion also just an approximation. So here what you get is an estimation. So similarly, we get an estimation for V2 also, right? So let's say it's a different function. So let's take it as G2. Now my problem is use this T1 and T2 and estimate capital T. Okay? This is where I should do fusion. If I ask you what is your solution, I'm pretty sure that many of you will say, why don't you take the average? Yes, that is one method. You can get T1 plus T2 and multiply each of them by 0.5, right? Same as dividing by 2, and you get a good estimation of the ground truth, right? But what you are actually trying to do here is we make a big assumption here, right? So please keep that in mind. When you are doing this fusion, that is average, I call this as the most simplest fusion algorithm. You make one assumption. Can you think about that? What is that assumption will be? Yes, we are assuming that both my sensors are performing equally, right? That's how this equal weighting comes. But if you really see all these sensors, or for that matter, if you see those algorithms that I have shown you earlier, sometimes we find one algorithm is better than the other algorithm, or one sensor is better than the other sensor, right? So if you have some idea about how much error that you are getting from each of them, then we can go for, instead of just averaging, we can go for weighted averaging, right? So if you have some idea about how the measurement error in each of these sensors, now if you take the sensor 1 has a variance or standard deviation of sigma 1, and sensor 2 has a standard deviation of sigma 2, you can see sigma 1 is less than sigma 2, right? Which means sensor 1 is more reliable than sensor 2. Then we can mathematically prove, rather than only selecting sensor 1, even if you are fusing another sensor with weaker performance, you can get better result. That can be mathematically proven, but I am not going to do it here. So basically, we get the weighted average, right? Uh, so what we are basically trying to do is, we are trying to minimize the estimation error covariance, right? And we can prove that you get the minimum estimation error covariance when the estimation is weighted by the sigma 1 and sigma 2 like this. So we get the weighted average where uh, we can write it like the actual or estimated value of t is equal to, now just think, just using common sense, right? Sigma 2 is larger than sigma 1. So which is the sensor which has to be trusted more? It is the one with less sigma 1. So if you can weigh the first sensor with sigma 2, right? Because sigma 2 is larger. But if you can use that larger value to give more weight to the more accurate sensor, then you can develop a small equation. But this equation was not developed like that. This is mathematically proven. What you try to do is you get the error covariance and prove that you get the minimum error covariance if the weight is like this. So let us see what is the equation. It will be sigma 2 squared divided by sigma 1 squared plus sigma 2 squared, right? That is the weighting term for the first parameter, right? Which is T1 plus, then for the other sensor, we will weight it with sigma 1. So it is interchange, you can see, because we have to give less weightage to the sensor with more high variance, right? So it will come like this, okay? So this is also a very simple fusion algorithm, and this works very well in some applications as well, right? So only thing is you have to do experiments and find what is sigma 1 and sigma 2. How do you find that? You measure the same thing again and again, try to find out. So for that you need the ground truth, right? So you need more calibrating instrument, and you take measurements, get the error, then using the error value you can find the standard deviation of the error, right? Very simple. Okay, now let us take another example, right? This is a different way of doing the fusion. Now, in the previous one, we were mainly focusing on the error, right? Now, here, I would like to take that gyroscope-based example, because we have seen many examples that I have done using gyroscopes and accelerometers. So let us take that mobile robo or the fetal monitoring gyroscope example, right? Let us take the robo example, right? So from accelerometer, you get 3-axis data, AX, AY, AZ. And from the gyroscope, you are getting the rotation about the 3-axis, GX, GY, and GZ, right? Now, suppose you mount this on a mobile robo, which is moving, right? And you want to estimate certain parameters of the robo. Most of the time, you want to estimate the location of your mobile robo, right, in a spatial domain. So robo coordinates, right, with respect to some position. Let's say it is something like x is the x coordinate, y is the y coordinate of the robo with reference to some axis, and z is the z coordinate. In addition to that, you may want to estimate the velocity of the robo, right? So x dot y dot z dot, maybe the acceleration or deceleration of the robo, right? So like that, you can put all the information that you want to get, right? So now you have two vector. One is the measurement vector. The other one is the state vector. We call it as state vector. So what we have to do is, we have to, given these measurement, we have to estimate these states, right? Now to do this, so let me call this vector as capital Z. Let me call this vector, right? So this 9 into 1 vector as X. I need, let's say I find some relation between X and Z, right? So suppose these measurements are given as a function of X. But not only that, when you are taking measurements, always you are getting some environmental or whatever electronic or whatever noise added, right? Maybe reading errors. For example, if you are taking it to a microcontroller like Arduino, there will be quantization error, right? So all these can be modeled as noise. So that also will be added to this data when you take the thing, right? Otherwise, this can be solved like a normal equation, right? There are few unknowns. If you can find known the many number of equations, then you can solve. But these problems are not like that, right? And if you are really fortunate, you will be able to model this problem as a linear problem. So instead of having a function like this, you may be able to model it as a matrix multiplication, right? So the matrix, this H matrix, will transform the state vector X into the measurement domain. Okay. So as an exercise, if you want, you can try to write this H for that temperature example, right? Now what we can do is, we initiate X with some initial values, right? Maybe some random values, so you can put them as 0. Then by substituting it to this equation, you can calculate Z or estimated value of Z, not the actual Z, but an estimation. Then what you do is, you can find the error between the estimated measurement and actual measurement, right? Because actual measurement you are getting from the sensors. And then what you can do is, use that error in an iterative manner to keep on updating X naught, right? So this phase is called as predict. This phase is called as correct. So these are called as predict correct algorithms. You predict Z and then correct X. Predict Z, correct Z. right? One of the most popular example in this predict correct algorithm is the Kalman filter algorithm. Some of you may have heard, because Kalman filter is theoretically proven to be the most optimal predict correct algorithm. But of course, with lot of assumption, right? For example, you have to make assumption that noise is Gaussian and various things are there. But I just want to give you an idea. This is the way that we do it. Right. Now let me take that army person tracking problem again, right? So there you have the body frame with respect to the inertial frame, and then you can model it like this. Right? I don't want you to go through this equation, but just to give you some idea, right? Some problems are very easy to be modeled, some problems are very complicated to be modeled. But actually speaking, this model is very easy compared to that spherical robot, because in spherical robot, we got huge matrices, right? But in these problems, you will end up with more smaller problems, right? Or smaller matrices. So what I want to recommend you is start modeling the real world problems like this, right? That will take you very far rather than using libraries written by others. Okay. Now we are going to consider another area, and I will stop from that. Use of probability theorem in sensor fusion. Right? I just want to do one example and show you, because that feels a different flavor. Right? Because in most of the advanced algorithms that you find in computer vision and various other applications, this is one of the mostly used approach. Use the theories in probability. And also there is another theory called as belief theorem. It's slightly different from probability theory. Now, one of the things that you may know about probabilities, which you may have happened to do in O level, is the conditional probability and the Bayes theorem. Right? Conditional probabilities, I think you have that problem where you put a marble into a bag and then take a red color marble and blue color marble, and I think you can recall, right? So this says, right, probability of an event A given that event B has happened is equal to probability of uh, event B given that event A has happened into probability of A happening divided by probability of B happening. Right? That's what called as Bayes theorem. Now let us take a very simple example and try to understand this. Right. For that, I'll be using a very common problem these days. All of us are nowadays hearing about PCR test and, let's say, antigen test. Right? We always hear that someone gets PCR positive or antigen positive. We hear stories really like, I got PCR positive but not antigen positive, and also the other way, right? I got antigen positive but not PCR positive, right? Because all these are sensors. All these medical tests are also performed based on sensors, right? So if I take PCR test as my sensor 1 and antigen test as maybe sensor 2, right? There are two possible events for each of these tests. Of course, you can take it as a continuous variable also, but for our easiness, we will take it as a discrete event, right? PCR positive or PCR negative. Similarly, for the antigen test also, you can get antigen positive or antigen test negative, right? Now, how we can relate this? Of course, there is another thing which is very important. That is the most important thing, not the test, right? Whether you are COVID positive or COVID negative. So let us consider that also as a discrete event, because that is what nowadays happening. No, nobody says that you are this much COVID positive, but they say yes, you are COVID positive. No, you are not COVID positive, which is not the reality, right? So please keep that also in mind. So now how to put this data into the previous equation, or how can we combine these two sensors when two sensors say two different things? How can I interpret that? Okay, let us take a sample of patient who has already got COVID, right? Because before putting these PCR testers and antigen testers, all these techniques to the market, they have to do this testing, right? So what they do is they select a sample of people who are already COVID positive, right? So first they select that. Then perform PCR test for all of them and find the probability of them getting positive for PCR. Now you may have the thinking, because of what you hear these days, if you have COVID, yes, your PCR should get positive, which is not the case, right? Sometimes you may be COVID positive, but your PCR can be negative, right? So you can easily find this probability value. You just have to count the number of people, and usually it will be a high value because these tests are very good. So let's assume that it's something like 95% accuracy or 0.95 probability, right? So it has some value. Similarly, you have to perform this test for people who don't have COVID and find out how much they get positive, right? So that is the other thing. And also, I can now write the probability of COVID positive given PCR. So that is what we want to find, right? Earlier we find if you are COVID positive, what is the probability of you getting PCR positive? That we can find by an experiment. Then here is the test. Suppose someone got PCR positive, can I find the probability of that person is COVID positive? Yes, you can simply use this equation because I know this value. So I can write this is equal to probability of PCR positive given COVID positive, right, which will come here, multiplied with probability of COVID positive. So if it is a time like this, it is a very high value, right? Actually, what this term means is if you take randomly 1,000 people from the society, you can find how many of them are COVID positive and COVID negative. From that, I can take this value, right? Or sometimes we put our belief also there, right? If it is a period like this, we will put a little bit high value there because there is a possibility that there can be people. Similarly, I can write a similar equation. You may ask what has happened to that division term. So here what you should get is probability of PCR positive. Does that make any physical sense? I hope no, right? And probability of PCR positive. Of course, you won't find, but it is not that important. So we represent it by alpha, right? 1 over that will be represented by alpha. Similarly, I can write the equation for COVID positive given that you are antigen positive, right? So we can write a similar equation. Now here I will put the beta term to represent the probability of antigen positive, and then I can write the same equation into P COVID plus, right? Yes, okay, this into P COVID plus. Right. Now, the question is how to fuse these two sensors using this. The question that I have to ask is, depending on what has happened, what is the outcome of both tests, right? For example, PCR also positive, antigen also positive, right? Then what is the final outcome that we can come by combining these two sensors? I can write it like the PCR positive, right? Antigen positive. So both event has occurred. So suppose someone you test both and both came positive. Still there is a possibility that he don't get COVID, right? I mean, always we have to leave that chance, which may be very small one. So what is the probability of someone having COVID when both tests comes positive? How do we calculate? If those who have done probability and statistics know, if this test is mutually independent from this test, I can break this equation into two, right? Which is P COVID given PCR multiplied by the antigen. I hope that is enough to give you some basic idea about different types of sensor fusion basics. And believe me, even when you are go to very high level, you are using them, right? So basically we use things like Bayes theorem, then Dempster-Shafer theorem. You can search on internet. This is also widely used for sensor fusion, right? And also Kalman filter is one of the most commonly used, and also extended Kalman filter. Extended Kalman filter comes when your the measurement to state transformation is not linear, right? When it is a nonlinear transformation. So in such cases, we are using extended Kalman filter. That also a predict and correct method. And then we use things like particle filters. Particle filter is something which is very widely used for robo navigation. There, what we do is, if I brief you on what is happening there, you just now in Kalman filter, you may remember, we have started with one initial state, right? We assume X naught is something and then go predict and correct. In particle filters, we start with assuming large number of solutions, right, which are called as particles. Then we calculate the forward probability, and eventually some of these particles will vanish from your picture, right? And finally, you will end up with converging into your correct location, right? So I will show you a video which is going to demonstrate that. Next, let us
So here is a floor plan of an environment where robot has range sensors, as indicated by the blue stripes. Those use sonar sensors, which means sound, to range the distance of nearby obstacles.
actually what you see as these red dots are the possible places where this robot can be, right? Because this robot is actually here, but suppose you want to find out where you are, because at the initially suppose it doesn't know, right? So you put all these dots everywhere, which represent your belief that you are at any of these places, right? So initially you believe that you can be anywhere. For example, think about when there is a power failure, right? You are trying to go in your home, right? You don't know where you are, so you can believe you are everywhere, right? But when you go and touch some door or something, then your belief will increase. So the same thing happens here, and you can see some of these particles will vanish with time, right?
And it has to use these range sensors to determine a good posterior distribution as to where it is. But the robot doesn't know it's starting in the middle of the corridor. In fact, it is completely uncertain as to where it is. Now the particle filter represents this using particles. Each of these red dots, of which there are several thousand here, is a discrete guess where the robot might be. It's structured as an x-coordinate, a y-coordinate, and also a heading direction. And these three values together comprise a single guess. But a single guess is not a filter. It is the set of several thousand of such guesses that together comprise an approximate representation for the posterior of the robot. So let's start the video. In the beginning, the particles are all uniformly spread, but the particle filter makes them survive in proportion of how consistent one of these particles is with the sensor measurement.
Some of the particles which are not agreeing with the sensor measurement are getting vanished, right? And most particles are getting concentrated at two different positions because this building is symmetrical.
The robot has figured out it's in the corridor, but two clouds survive because of the symmetry of the corridor. As the robot then enters one of the offices, the symmetry is broken and the correct set of particles survive. Let me play this again. The essence of particle filters is to have these particles guess where the robot might be moving, but also have them survive using effectively survival of the fittest, so that particles that are more consistent with the measurements are more likely to survive. And as a result, places of high probability will collect more particles and therefore be more representative of the robot's posterior belief. Those particles together, those thousands of particles that are now clustered at a single location, those comprise the approximate belief of the robot as it localizes itself.
Important thing here is, now in the Kalman filter, we started from one possible solution and then try to converge to our answer. But here we start with multiple positions and then we try to converge to an answer. So if you get this basic right, you can even go and understand other algorithms. For example, there is another powerful algorithm called as genetic algorithm. Although people are trying to relate it with the human evolution and various things, no, if you really get the fundamentals, you will see that they are also connected with this. So the important thing there is, if you have that vision, you can develop your own algorithm, right? That is where we should pitch at. And also, when these relationships are non-linear, we use some other technologies like deep learning. Some of you may have heard, right? So when the problem domain is non-linear, deep learning is used, right? So there are many more methods which are available for sensor fusion. But what is important is understand the very basic fundamentals of them. Then you also will be able to develop one day for sure your own algorithm, right? And that will be the day that I will be rewarded for this lecture, right? If some of you can come and say after some time, so I was able to develop that algorithm, right? After listening to that lecture, that is the best reward that I can have, and it has happened in the past. And I'm pretty sure that some of you also will definitely give that award to me, right? So understand basics, that's very important, and always try to apply yourself. Try to see whether the problems that you see around you, right? Fortunately, in Sri Lanka, we live in, among problems, right? There are a lot of problems around us, which is very fortunate. So you try to solve them using what you have learned, right? So I think we will stop it here. So thank you very much for your attention. And as I mentioned again, hope that you will give that reward to me one day. And most importantly, these days, stay safe. So I wish you all the best in your future careers. Okay, so if there are any questions, I would like to give the answers or at least guide you towards answers. So thank you
Thank you
very
very
much
much,
again.
sir, for that very informative and interesting session. I hope our participants were able to get an exposure to sensor fusion, why, when, and where to apply it, and especially its applications in robotics. They have also sent us few questions through the link we provided. So, and if anyone has missed sending the questions, can now scan the QR code and send your questions to us. So, sir, the first question is, what are the methods that we can use when localizing something? I mean, other than GPS and gyroscope.
Okay, can you hear me? Yes.
Yes, sir.
It's a very good question, because always you have to look for other possibilities. Now, for example, in the animation that I have shown earlier, they were using, because it is an indoor environment, so they can always get reflection from the wall, right? So they were using ultrasound sensors, or some sensors which can measure the distance from that robot to the wall, and then use that for localization, right? So that is one method. And also sometimes in large fields, right? For example, once we were handling a problem where we want to track the football players on the ground. That also a localization problem. There, the solution we proposed was we placed sensors around the ground, because we can't attach sensors those days to the players. And then what we were doing was we were transmitting signals from those sensors and receiving signal from a device in the player, and use that to get their location. And also vision based, right? For example, I remember, I think that project was again done with that spherical robo group. We were using the camera. It was not successful, I should say. We were using the camera, and then I mean, it was mounted on a quadcopter. So by looking at how the camera image changes, right, up to some success, we were able to locate the position of the quadcopter, right? So by looking at how the video is changing, so like that, there are a lot of ways where you can estimate the same thing. The most important thing is, or most beautiful thing in engineering is, from problem to problem, right? There can be different techniques, or you can combine all these techniques and get better output. I hope that I have given some answer to that. So my simple answer is be clever.
Thank you, sir. So the next question is, how do we use machine learning to optimize sensor fusion, or is it overkill to use machine learning to do sensor fusion?
Which problem? The one I see on the screen?
Sorry, it is the second one.
All right. Can you tell it again?
So can we use machine learning to optimize sensor fusion, or is it overkill to use machine learning to do sensor fusion?
Actually speaking, machine learning contains very broad areas, right? For example, I was referring this Kalman filter, and then genetic algorithm, particle filter. All of them are sort of optimization algorithm. They are trying to minimize the final estimation error, right? In all of them in different ways. So what's that question again? So optimization is part of machine learning. I don't know whether that will give an answer.
Or is it overkill to use machine learning to do sensor fusion?
Yes, I mean, we are using machine learning to do sensor fusion, right? Although, I mean, some of them looks like mathematics, that's also part of machine learning, because these subjects are now having a lot of overlappings, right? So there are classical mathematical techniques as well as machine learning. I told you that we can use deep learning for doing it. Okay.
Yeah, thank you, sir. So the next one is, how do we deal with asynchronous data in fusion algorithms? That is, if we have two independent sensors with a sampling rates of 100 kilohertz and 30 kilohertz.
Actually, very good question, right? Now, in one, you are getting data very fast. In the other one, you are getting data at a slower rate, right? So let's take the 30 kilohertz one. So between two samples, there are missing places, right? So during that time, because when you are, I don't know whether I can draw it. Okay, I'll just try to explain, right, using words. So in the 30 kilohertz one, the distance between two samples are high, right? So the reliability that you put on the 30 kilohertz one in between the two samples will go down, right? Now, let's say you are combining these two data, but the 100 kilohertz data, it has more samples in between two samples in the 30 kilohertz data. So in between the two samples, you can give more weightage to the 100 kilohertz data. That is one technique which I can directly see, right? So when the two samples are coinciding, then you can give equal weight, or depending on the sensor type, you can give weightage. But when in intermediate points, you can give more weightage to the 100 kilohertz sensor, right? So that is one way of handling this problem. Okay.
Yeah. Thank you, sir. So the next one is, what are the reasons for sensor fusion failure? I mean, even Tesla haven't been able to use those techniques in their products perfectly.
Yes, as I mentioned, right, always there is a chance of failure, because the best sensor in the world is going to fail, right, at some point. That is where the subject of sensor fusion is more important, because even even when the best sensor fails, right, you have other sensors which will compensate for that, right? The chance of all the sensors failing together is much less. So what I can give there is the probability of fusion algorithm fails is much less than individual things are failing, right? But of course, the fusion algorithm also can fail if you don't have the correct values. Now, for example, if I take that simple problem of combining two sensors, right, which I have demonstrated, multiplying by that sigma 1 squared and so on. If you don't calculate, or if you don't have a proper noise model, or if the noise pattern changes while you are taking measurement, for example, when your sensors get heated, your noise model can change due to thermal noise. So in such case, sometimes sensor fusion can give you worse result, right? So you have to keep, I mean, always when you come up with the design, the first thing that you have to do is you have to criticize your design and try to identify where it can go wrong, right? Unfortunately, most of us, when we come up with the design, because this happens in projects always, when you come up with the design, we always try to defend our design, thinking that you are going to sell, or we are not marketing people, right? As scientists, we always should accept anything can fail at any time. And what is important is we analyze properly and identify where something can go wrong, and then take measures to minimize that. We can't get rid of those things, we minimize, right? I think that is the best answer I can give. And thanks for asking that question, because it's a very important question.
Thank you, sir. So the next question is, e-compasses don't need to be horizontal to the ground anymore. Even if they are tilted, they show us north. Is sensor fusion used here? What sensors are those?
Actually, the last question, I'm not sure about the answer, right? What sensors are those? But I know that they are using sensor fusion, because in one or two of the examples that I have shown also, this fetal monitoring problem, and also this tracking problem in Army. One main problem that we have is all these sensor orientations are getting different, right? So there are, I mean, we have to employ techniques to identify or establish the frame also. That's why I told that spherical robot problem was a huge challenge, right? Because it is always changing, right? So, but actually doing that kind of problems are, I mean, one method is you can buy some sensor like this, but also think how you can solve a problem like that yourself, right? For example, in gyroscope, one of the main, sorry, not gyroscope, accelerometers, one challenge we have is, because always this gravitational thing is there, right? One sense, if you have it flat, right, then the z-axis will have this 9.81 thick. But the problem is when you are wearing it on your body or somewhere, we are not guaranteed that it's always vertical, right? So that gravity goes to other axis also. So we should have techniques to, I mean, get rid of that. And usually we do axis transformations. So that kind of algorithms are there, right? Unfortunately, I don't know what sensors are there inside it because I haven't seen that.
So thank you, sir. And the next one is, do we need powerful processors to process sensor fusion inputs? Seems like those algorithms are complicated.
Yes, again, a very good question. Now, sometimes you can develop very complex algorithm, right? But when you have to put it to a smaller processor, like in the spherical robot problem, we had the challenge of putting that to that DSP board, right? Then we have to identify other interesting techniques. There are a lot of good research, right? For example, I'll tell one example. If you take Kalman filter, the Kalman filter algorithm contains matrix inversion, right? The algorithm itself contains matrix inversions. But when you put it to a small microcontroller, sometimes you can't put that to the microcontroller because it is very complicated. So what you do is you run the Kalman filter in a machine and get it converged to some value and then use those values in your hardware, right? But definitely it will not give the best result because in a Kalman filter, we have something called as Kalman gain. The Kalman gain is always iteratively calculated. But in some of the applications I have seen, they calculate the Kalman gain, what is, just assume it is some parameter. That parameter is calculated in the computer and then directly transfer it to the hardware because of this complexity, right? So this also, I think that is one solution we can give. The other solution is we can improve hardware. For example, nowadays, many algorithms which need powerful processing are using things like GPUs or the FPGAs, right? Field programmable gate arrays. They are widely used in robotics now. So don't think only we can use processors, right? Processor is one thing, and FPGAs is becoming very popular in robotics area because of their fast processing, especially things like I have shown you one example at the very beginning, that vision-based navigation robot. They are to process the stereo camera data, because stereo camera you get a lot of pixels, right? And to process them, we had to use FPGAs, then extract some information and pass that to other devices. So we can use parallel processing, right? For example, just to do matrix inversion, you can use one processor. So there are a lot of techniques that we are using for doing that kind of things. Okay, I think.
Yes.
Yes.
Thank you, sir. And the next one is, usually when there are more sensors, there is more noisy data. What are the methods commonly used in eliminating those noises?
Of course, even though you have, I mean, you may be assuming that all these noise get added or something like that. But when there is more sensors, it doesn't necessarily mean more noisy data. right? Because there's something in that question. What happens is if you have a lot of noisy data, when you get the, more and more sensors, you can get rid of some of these noise. The best example is, I haven't shown you any examples here, but we have done some research in EEG signal analysis, brain signals, right? EEG signals are one of the most difficult signals to be analyzed because they contain a lot of noise, unwanted information, right? Usually, we take around 100 ensemble, we call it as ensemble. So it is not directly sensor fusion, right? We take windows of EEG, and then we got the ensemble averaging that will give us, get rid of the noise, right? Actually, mathematically also we can prove, some of you will be doing subjects in future like random signal analysis, how this these kind of things will help us to eliminate. So more sensors you have, there's a more chance of getting rid of noise. Okay, thank you for asking that question, because that is very important question. Right?
Yeah, thank you, sir. And it seems like next one is the last question. Sir, I have heard that drones are used this sensor fusion method to be stable in the air by determining the wind direction. Is it true, sir?
Yes, not only wind direction, right? There are various other things that you are taking, and also there, to make it more stable, you introduce a lot of redundancies, right? So more measurements you have, you can make it more stable. And also not only sensor fusion, right? There are more advanced way of controlling also. Now, for example, the traditional control techniques, I think you will learn in this workshop series, right? PID controls and traditional controls are there, but then there are more advanced controllers which can make the drones very much stable, right? At one time, actually, I think if you ask from Dr. Maitripala, right, they have one research paper. They are theoretically proving, right, that the algorithm that they are proposing is the best in the world, not in Sri Lanka, right? Best in the world. So if you want more details, you can ask from Dr. Maitripala if you happen to know him, right? So yes, we can use various things to make it more stable. Not only sensor fusion, but sensor fusion also used.
Thank you, sir. And yeah, we have received another one question.
Right.
When fusing numerous sensors, there can be delays in receiving data between each source. How do we tackle this problem?
Yes, again, a very good question. Actually, this is a research problem also, right? Not only delayed data, some data get completely missing, right? For example, if you take in the Kalman filter, on the left side, you have all the sensor data, right? And sometimes one of the main challenge we have is some of these measurements get missed or they get delayed, right? In such scenarios, I think what we are doing is, right, when you don't get the measurement from a particular sensor, then what you do is you assume, you will assign maybe the last value you have or some average value, statistically average value that you have calculated, you will keep it. But then for each measurement, you are assigning a weight value, right? Even in Kalman filter, you can see for each measurement, we are assigning a weight, right? That weight can be reduced if you completely miss the data or if you suspect a particular data is not valid, then you can always reduce the measurement, because in the Kalman equation, when you study, you will learn there's another matrix to model the noise or noise model, right? For example, we we define a matrix called as noise covariance matrix, measurement noise covariance matrix. So what we usually do is when a particular data get missed, we increase the noise covariance value. So we give less weightage to that particular sensor. And also if it comes delayed, then then there are other techniques, right? This is again a very interesting problem. Actually, we have one or two PhDs in our department also who has worked on this. I think Dr. Lilanta's PhD was in an area like this, where how to develop controllers using delayed information, right? For example, when you are using a controller, you get some sensor information delayed. And then what Professor Lilantha has done in his PhD is how to use those delayed information in your control algorithm, right? So for those things also, there are established techniques, and these are very interesting research areas as well. Okay, thank you for those very interesting questions, right? Because it's always discussions of this nature will take you to the next level.
So yeah, thank you very much, sir. With that, the Q&A session is concluded.
Yeah, thank you.
So before going further, I have a request to be done from all the participants. Please fill the feedback form and give us your valuable feedback. You can now access it through the link displayed in the chat box. Also, you can scan the QR code shown in the screen now. And now we are going to announce something really interesting for you all. For that, I invite Mr. Udula Ranasinghe, the Secretary of Robotics and Automation Society of University of Peradeniya. Over to you.
Thank you, Utpala. First, I would like to thank Dr. Janaka Wijayakulasooriya for this very inspiring session about sensor fusion. Now, I would like to take a couple of minutes to give you a brief introduction about the competition. So during our first year, we had this great opportunity, I think for 16 and 17 batches. There was a mini project to design and implement a line following robot. But unfortunately, due to this pandemic situation, that experience is drifted a little bit for our junior batches. So we thought of organizing this competition to design a line following robot using robot simulation software. So we believe most of you took part in our webinar sessions, in which we mainly focused on robot around how to design, implement, and program our robot using robot. So they will provide you necessary knowledge and good guidance to develop your idea. So, but for those who haven't participated, don't worry, we have uploaded them to our YouTube channel, so you can access whenever you feel necessary. So, when developing your robot, we suggest you to come up with your own idea instead of searching through the web from the first instant. So, in that way, you can develop your creative new ideas as well. So, all the participants will be awarded with participation certificate, and winners will be also rewarded with valuable prizes. And more details about this competition will be uploaded to our IEEE official website. So you can go there and download those documents. And also we are planning to upload simulation file contains line paths in robot simulation software. So you can download them and straight away use them to create your robot rather than spending your time to develop those worlds. And so from today onwards, you can create your groups and start brainstorming and use your free time to work on your brilliant ideas. So that's all I have to add. Pretty much, have I missed something? And also, but for people who fill the feedback form, please give your email. So if you are hurry to get those webboard files, we can email you privately. And that's all. I wish you all the best. Thank you. Upala?
Thank you, Dylan. So now we have almost arrived at the end of today's session. I think it's time to conclude our webinar, which, as you all experienced, was a huge success. On behalf of our society, I would like to thank Dr. Janaka Wijayakulasooriya for joining us today. Dear sir, please accept our token of appreciation presented to you by the Robotics and Automation Society of University of Peradeniya.
Actually, thank you, Utpala, for this appreciation. But honestly speaking, this is not enough for me. Right? What I really want is what I mentioned in the presentation. That is the best reward that I can receive. You use these things in your research. Thank you.
Yes, sir, sure. We'll give you what you want, sir. Furthermore, I should not forget all the participants who attended this evening. Without you, this event would not have been a success. Finally, I would like to thank all the members of the Robotics and Automation Society who worked hard towards the success of this webinar. Before winding up this session, I would like to remind you all that the second day of Phase 2 of Robotricks 2021 webinar series is scheduled to be held soon. There, we hope to give you the knowledge about estimator design. Join with these upcoming webinars as well to gain extensive knowledge in the field of robotics. Now it's time to conclude this webinar. Hope to meet you in the next day with the same enthusiasm. Don't forget that in the end, you will be creating your own robot. Stay safe, everyone, and have a good night.